Hello dear friends, welcome to the third session of this course. And in this session, we want to in this session and the next two sessions, which makes a total of 3 sessions, we want to focus together on how simple projects are done with microcontrollers, and we'll work on some projects so that later you can see how complicated it could have been if you had to design a circuit for them and how easily we can do it with a microcontroller. In the previous 2 comprehensive sessions, we also diligently tried to make absolutely sure that you became fully and completely familiar with microcontrollers and their associated software, and that you're now comfortably proficient enough to understand precisely what's happening in any given project, as long as you possess its corresponding code and circuit diagram. I sincerely hope it's been incredibly useful for you. Well, in this session, what I've planned for you is a good starting point so that we can get more familiar with the programming environment as well as with projects. It's a very simple project, but at the same time, it might be interesting. The light dance project, which we've seen in the market in both very simple and even much more advanced forms. But now we want to implement a very basic light dance together. Something simple but perfectly suitable for learning and for us to see exactly what's happening. So what do we need? As you know, we don't need any additional circuitry for the microcontroller. For this project as well, we only need the microcontroller itself and a few LEDs to connect together. In the Proteus environment, just like I showed you in the tutorial, we need one AT-MEGA32 and a few light-emitting diodes commonly known as LEDs, which we can conveniently choose in a variety of different colors. For example, we have the vibrant green, the striking red, and the calming blue. Alright, we place the microcontroller itself in the center. And now the microcontroller itself provides us with 32 pins or 4 8-pin ports for input and output. But to keep our code from getting unnecessarily messy, we'll just use one port. For example, here we consider port A and connect 8 LEDs to it. Alright, we bring in the LEDs one by one, and you can rotate them using the plus and minus keys on the keyboard. And, well, these are just the tricks of each software that you'll gradually get the hang of. For example, I'll place 3 green ones. 3 red ones and 2 blue ones. And we will now start connecting these essential components to port A of the microcontroller unit, which is a crucial step. Sometimes we notice that our connections aren't coming out well. We can move the components around a bit, and at this stage, drawing the circuit is completely a matter of personal preference. But after that, designing the PCB is the opposite. It has to be something entirely scientific and professional. With just a couple of clicks, we can also repeat some connections like here. So this is our initial drawing, and it's something very simple. We have a microcontroller and 8 LEDs, and we want to turn them on and off in different ways using various algorithms. Now we enter the CodeVision environment. At this point, you should already know how to create a new project. So what we need here, and you've probably guessed it, is to set those pins to output mode, and that's basically all we need to do in CodeWizard. That means we select our microcontroller, and then we set those 8 pins to output mode. From port A, we then proceed to meticulously generate our comprehensive and optimized code. As I mentioned before, it's better to use the same name in all 3 steps when creating the files. Now let's enter the programming environment. The point is, in these 3 sessions, you're not going to become a professional microcontroller programmer, nor are you going to fully learn the C language. And if anyone tells you that you can learn it all in 3 sessions, especially 3 sessions of just 15 or 20 minutes each, without putting in extra work elsewhere, they're not being honest. And what I've planned for you is to make sure you get the maximum familiarity, and overall, this course is meant to be a practical, hands-on course. The explanations for this were given to you in the first session. The purpose is that if you're interested and you enjoy it, this will serve as a starting point for you to continue down this path. Now, I'll also try throughout this project setup to provide you with as much explanation as possible about the programming aspects. Well, in the C programming environment, there are a few very important sections overall. First of all, let me say that at the beginning of every code, we usually have some comments in our code. In every programming language, you can add some comments. Here, comments mean additional explanations. These are explanations that the programmer writes, but they have no effect on the code's execution. For example, here CodeVision highlights them in blue for us, so they're clearly distinguishable. With these symbols, we can create multi-line comments, and with these two symbols, we can make a single line comment. And as I mentioned, since comments have no effect on the code later on in your own projects, or generally when creating a project, you can completely remove them to keep the code from getting too cluttered and to make it more readable. And if you want, you can keep them to show some explanations. Like here, it's giving some English descriptions about what version of CodeVision it is, the date, which microcontroller is being used, its frequency, and similar details. So you can completely remove the comments. Right now, this section can be deleted. These are removable. All these blue parts can be deleted. So that was the explanation about comments in the C language. After that, we have an important section, which is our libraries. What exactly are libraries typically used for? They are primarily for having some readily available pre-written codes, whether it's the specific software application we're actively working with, or in the particular case of hardware, the essential component we're currently working with. All of these have a set of instructions. There are some specific commands, and they gather them together as a library so that for us, the end users who are going to use them, nothing unusual or complicated is expected. So these libraries are a set of ready-made commands that we use. For example, here where your microcontroller is Mega32, there is a Mega32 library related to this microcontroller that it automatically imports. Or for instance, as we saw in the previous lesson, and we also need it in this lesson, we have another library called delay. This library has two very important commands. There's delayums and delayus, which can create delays for us in milliseconds and microseconds. If you want to create this delay normally, you might need several lines of complex and rather strange code to achieve it. But for example, CodeVision has done this for us in the form of a library, and it handles it itself. We just tell it how many milliseconds or microseconds we want to delay here. So libraries in the C language are included like this using the include command, and that's how we use them. As we continue, we have a function called the main function, which is a standard in the C language, and basically our code starts executing within this function. That means outside of this function, we have the libraries, and as it's shown here, we can define some variables here, and then once we enter the main function, our code starts to execute. From the very first line of the main function, we can have executable code, and usually inside the main function up until the main loop of our program, we execute some initial commands. Like what? For example, here we set the pins of port A to output mode. This is a command that should only be executed once. When the microcontroller is powered on, once it turns on, it executes these commands once. Any configuration that needs to be done, any settings that need to be applied, all the register configurations, these are all done in this section, and then we reach the main loop. In the main loop, our code starts running infinitely until the microcontroller is reset or turned off and on again. Or sometimes it happens that we want to completely exit this function and have the microcontroller stop entirely, no matter where it is. But in any case, it only returns to the beginning of the main function if we reset the microcontroller or turn it off and on. Otherwise, it just falls into the main loop. And now the algorithm we've designed for the program will run infinitely. So now you should have a general overview of a C program as a whole. This isn't specific to microcontrollers. In general, in programming, specifically in C language programming, we follow this process. Let me summarize it very briefly. Our libraries are included. Our variables are defined. We have a main function. In the main function, some initial tasks are done, and then we enter a loop. Now, as the program becomes more advanced, these steps become much more complex. We also add our own functions. We might have several loops. We have one loop where a series of tasks are performed. After that, we exit and enter another loop. Again, our tasks are carried out there. Then, for example, it goes into another loop that continues indefinitely. So this is the general overview of the C programming language. Now here we've used the code wizard to do our initial setup. We've also imported the necessary libraries, and now we want to control port A the way we want. Alright, so to control the ports on the microcontroller, this is where the discussion basically starts, so make sure to follow along carefully. To control a port on the microcontroller, we have 3 registers. Remember, I mentioned that we have a set of registers that we use to configure the hardware settings. Since things like setting pins to 0 or 1, or making them input or output, are supposed to be applied to the microcontroller's hardware pins, they each have their own dedicated register. And here we start introducing these registers. The simplest ones are for the microcontroller's pins. We have 3 registers: port, pin, and DDR. What are these 3 registers? Let me start from the right. With DDR, we specify whether a pin is going to be input or output. With port, we specify whether that pin should be 0 or 1. And with pin, if the pin is set as input, we read it to see whether it has been set to 0 or 1 from outside. For example, if a button is connected to it and we need to read that button, we use pin to read it. If we want to send a 0 or 1 command to an LED, we do this with port. And if we want to specify whether a pin should be input or output, we do this with DDR. Now if we go back up here, you can clearly see this. When we assign a value to DDRA, we're setting the pins of port A to output mode. Or here, where it's using port A itself, it's because it wants to set them to 0 or 1, and in CodeWizard we specified that they should all be 0. Now it's the same here as well. We've already handled our input and output configuration with CodeWizard, and now what we need is to use the port. Basically, the way to use these registers is to write this expression. Then we add A, B, C, or D and use it as needed. Now for example, here I want to use port A. I can use this port A in several ways. One way is to say, for example, set port A.0 equal to 1. What does this mean? It means set pin 0 of port A to 1. If I compile this code now, and once you have successfully loaded the program code into the microcontroller unit, you will clearly observe that the specific pins which are currently displayed in gray are not functioning as outputs. This means they are neither in a state of 0 nor in a state of 1. The pins that are blue and red mean they're currently set as outputs, and right now they're in output mode and are at 0. No value has been assigned to them. We set the first one to 1 and its corresponding LED turned on. So this is a simple example of port initialization. Now sometimes we want to initialize all the pins at once. In this case, an important thing to know is how different numbers are represented in the C language. Now, if I want to start with the simplest, we have binary numbers. Since our port A is an 8-bit port, it means it can take a value of 8 zeros and 1s. Look, our port A has 8 pins, and accordingly it can take 8 zeros and 1s and set them on these 8 pins. For example, when we say 0, it means an absolute 0. Even if there are 8 zeros in a row, it's still just 0. But when we go above 0, this concept changes. Now, to give you an idea about binary and hexadecimal numbers, if you're familiar with programming, you've probably heard about this before, but if not, I'll show you an example using the calculator in Windows. If you open the Windows calculator and open the side menu, there's a programmer section. In this programmer section, you can get more familiar with these numbers. The numbers we use in our daily lives are the ones we're used to. These are decimal numbers, meaning base 10. So what does it mean when we say base 10? It means our numbers go from 0 to 9, so we have a total of 10 digits. And so by putting these digits from 0 to 9 together in sequence, we form our numbers. Now in exactly the same way we have binary numbers. Binary numbers are base 2, meaning 0 and 1. And we just arrange a series of zeros and ones in sequence, and almost everything in a microcontroller is done using these binary numbers, and most of our assignments in programming are done in this way. After that, we have hexadecimal numbers, which are base 16. That means our numbers go from 0 to 15, but since after 10 the numbers become 2 digits, to avoid having 2 digits, they use letters instead. So our numbers go in order 0, 1, 2, 3 up to 9, and then A, B, C, D up to F. And basically, we have 16 digits from 0 to 15, which are used to form our numbers in the hexadecimal system. I'm just introducing these now so you can look into them yourself, because we haven't really done anything yet, and our video is already almost 20 minutes long. As you can see, the amount of material is much more than what some people might promise to teach you in a very short lesson. Alright, now let's move on to binary numbers. For example, let's say I want to turn on every other LED, so I need 8 zeros and 1s in a row. Well, actually not every other one. I want 2 LEDs to be on, then 1 off, then 3 on, then again 1 off, and then 1 on. This becomes an 8-part pattern for me. Now it's showing me the equivalent of these. It says this binary number has a hexadecimal equivalent. You see, as I said, our hexadecimal digits go from 0 to F. This is now a number in base 16. Its decimal base, meaning its regular number, is 221. Since our number is in base, our number is 8-bit, meaning 8 zeros and 1s in a row. It can have up to 2 to the power of 8 possibilities, which is 256 possibilities. That is from 0 to 255. I'm repeating these again, just to give you a sense so that you can look them up and learn more about them. Now here, our number from 0 to 255 has become equivalent to 221. Now we want to set all 3 of these states on port A and see how it works. First, I'm going to set its normal value. Okay, its normal value tells me that it's 221. I'm saying set the entire port A to 221 and it compiles this. Now it applies exactly the same intricate pattern for me on port A. As you can clearly see, we previously established a sequence of 2 on, then 1 off, followed by 3 on, then another 1 off, and finally 1 on. And from the very end it is distinctly showing us this precise pattern. Now our objective is to meticulously repeat this identical configuration, but this time we will be operating in hexadecimal mode, which is a different numerical base. Well, in C language, when we want to write numbers in hexadecimal form in a normal way, we just write the number itself. By normal, I mean in base 10, that is the numbers we use in our daily lives. Now if a number is supposed to be written in hexadecimal, a 0x comes at the beginning. For example, here where we have the hexadecimal number DD, what do we put here? We put a 0x and then DD. Now let's compile this code. And we run it. You can see that it's showing us exactly the same pattern. Another way we can represent numbers is in binary. When we want to show binary numbers, just like we put 0x for hexadecimal, we put 0b for binary and then write the actual number. So what exactly did I have here? I put a 0b and then here I said I want 2 on, 1 off, 3 on, off, on. 2 on, 1 off, 3 on, off, on. And I assign the value like this. These 3 numbers make no difference to this software. That is all of them, meaning from the beginning, whether we write 221 or 0x or 0b. And this binary number from the microcontroller software's perspective, all of these are the same number, and it breaks them down into binary and assigns them in order to the pins of port A. Now, if I compile this code, and if I run it here, you can see that the same pattern is being displayed for me. In some cases, well, using binary numbers can be easier. That is, as you can see, we can now clearly see which of the 8 bits of this number are 0 and which ones are 1. And for example, if I want to make a change, say I want these 4 in a row to be on. Okay. For example, I want it like this, 4 on, 4 off. You can see that its decimal value, for example, changes from 221 to 240. And well, this should be calculated, or in hex, for example, it becomes F0. But its binary representation is really cool and you can have complete control with it. For example, if I come and change this binary like this now, and if I compile this, you'll see that it turns on 4 LEDs for me. So in this way, we learned how to work with ports in microcontrollers and what numbers look like in the C language. We've also become somewhat familiar with the C language itself. I'll dedicate the end of this session to creating a very simple light show on the LEDs. So what do I do for this? This is so I can copy it and make my work easier later. I create a binary number with 8 zeros. That means that all of the individual LEDs are currently off right now, and then there will be a significant delay, for example, a period of 200 milliseconds, okay? I will proceed to copy this particular configuration and then make several additional copies of it for further use. Now what I want to do is make my LEDs light up in sequence. Well, in the first step, I'll say that all the LEDs are off. Wait 200 milliseconds. Now let's turn on the first LED. Wait. Bring the next two and light them. That means turn on the first, second, and then third. 4. And I keep repeating this process until the end. And this last copy is extra. So what do we have now? We're just putting a series of different numbers on port A with 200 millisecond delays, and this loop repeats infinitely. Now, if I come and run this code, you'll see that it starts turning on the LEDs for me in order. Now, this becomes your own exercise to try putting different numbers on port A, and you can create all sorts of other light patterns. For example, you could have it continue and turn off in order, or have every other one light up, or every 2, or you could have some other patterns like lighting up from both sides. These can serve as simple exercises and in a way a bit of play for you to continue with, so you get involved yourself and experience the enjoyment. Now let's see that this kind of light show is also sequential. Imagine how much more complex the circuit design would get if it had a more random pattern. But with a microcontroller, this is done so simply. And that's it for this volume of Samum. I hope it was useful for you. Until the next session, goodbye.